Hi, this is Mr. Markados. In this video, we're going to look at more of the net change theorem. And in this particular question that we're going to work on in this video, this is a AP free response question where the calculator is active. It's a pretty standard type of question. We tend to call this our rate in, rate out question. It's one of the main applications of the fundamental theorem of calculus and can be used in a lot of places. So it's not surprising we get asked about something like this. So, a water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. During the time interval from 0 to 18, water is pumped into the tank at a rate W of t gallons per hour. So that W of t function, we would call this our rate in function, water being pumped in. During the same time interval, water is removed from the tank at a rate R of t gallons per hour. So water's coming in, but also water is going out. And so the function R of t, we would call our rate out function. Okay, part A. Is the amount of water in the tank increasing at time t equals 15? Why or why not? Here's the problem. We spoke about this in class. You'll see it present in this problem as well. Many of the questions I'm asked about refer to the amount of water, how much water. But in the problem, we're not given any information about a function which represents the amount of water. We have a function for the water flowing in, so that's a rate function. We have a function for the water flowing out. That's also a rate function. Neither of those functions tell you about how much water you have. So pretty standard in this problem. I always urge students to do this. What I'm going to do is, before I even answer part A, I'm going to define a function and let it be the amount of water at time t. You could pick whatever you want because if you're defining it, it's your choice, but maybe I'll pick like A of t. So we'll say let A of t be the amount of water in the tank at time t. Maybe if we got like uber specific, what's t going to be? It's the interval that they're talking about, so from 0 to 18. You're better being specific than not, right? Especially if you're going to define your own function. Okay, is the amount of water in the tank increasing? So normally, when you'd like to know if a function is increasing or decreasing, such as this function, you would have to find its derivative, and then, I guess in this case, plug the time 15 into the derivative and see what the sign of the derivative is. Because when my derivative is positive, my original function is increasing, and when my derivative is negative, my original function is decreasing. So the question is, if that's A of t, the amount, who's the derivative? And it's interesting, and this is the most important thing about this problem. If you're saying A of t is the amount, then what we are saying is that the derivative of A prime of t, is the rate at which water is being pumped in, so W of t, minus the rate at which water is being pumped out. Remember, these are rate functions. So like to say that they are a derivative of somebody would make sense. But notice it's not just a singular function. It's the rate in minus the rate out. So depending on what the sign of W of t minus R of t is, that will tell me if the amount of the water in the tank is increasing or decreasing. So I would say then that A prime of 15 would be W of 15 minus R of 15. And if this is, of course, part A. So I need my calculator, and I did a little bit before here, so I'll show you. The very first thing I would do here on my calculator is define the functions W of x and R of x so that they're ready to be used. Right now, like that they're defined, and I'm looking to find the value of W of 15 minus R of 15, all I have to do now is actually type that into Desmos, which is why I would use Desmos pretty much all the time. So it's... And we'll see here, I'm actually going to do this. I'm actually going to type in the function W of x minus R of x because as we will see, that the difference of those rates is going to come up quite a bit. If there's too much on your graph, as you'll see, like I don't really want to pay attention to any of these individually at the moment. It's really just W of x minus R of x. So I'll hide those. but Desmos still knows what W of x and R of x is. So I need to find, so I'm going to do W of 15 minus R of 15. And whatever that is, I'm going to write that down on my paper. So I'm getting, let's see, it should be minus 121.09, roughly. As I mentioned to some of you, in terms of rounding, they're not too upset if you cut off some decimal places here. They don't need to see the entire value. Also here, right, the only thing I particularly care about is that the answer is negative, right? It's not that I care a ton about the numerical value to answer this question. So I got about negative 121.09. Now, this is a rate, so it should have rate units. They didn't ask for units, but maybe I'll just put them to be a little bit careful. So it's minus 121.09 gallons per hour, right? What would I say here to explain my answer? I have work to show it. By the way, I didn't show any plugging in of 15 to any of these expressions, correct? The reason for that is they know I'm using my calculator. To write that out is just going to waste my time. So I would say the amount of water in the tank at T equals 15 hours is decreasing because, right, this quantity is negative. Because at time T equals 15, the rate in minus the rate out is negative. You could write is negative or just less than 0. And that makes sense, right? If you think about that for a second, what that means is water is being pumped out of the tank faster than it's being pumped in. So you're losing water in the tank. The amount of water is decreasing. Okay, part B, to the nearest whole number, how many gallons of water are in the tank at time T equal 18? Notice they did kind of specify here, like, hey, give me your answer to the nearest whole number. That's important then I should give my answer to the nearest whole number. Here, I'm not too concerned about chopping my decimal places or where to round to particularly. So, okay, check this out, right? You have to think about this. When you integrate your rate function, you get information back about amount, right? Be careful here because your rate function is actually made up of two functions. It's your rate in minus your rate out. So I'm going to write an expression that's going to help me calculate A of 18. Notice they did tell me the amount of water that was initially present at time 0. So for part B here, I do know that A of 0 is 1,200 gallons. And I'm going to use that to help me find the amount at time 18. So, right, if I integrate my rate function, but my rate function is W of t minus R of t, it's not just like one function, but if I integrate my rate function between time 18, between time 0 and 18 by the fundamental theorem of calculus, what do I get? I get the antiderivative of this rate in minus rate out, which is the amount function. So the antiderivative is A, right? So I'm going to get the amount function at time equals 18 minus the amount function at time 0. Again, pretty kind of standard practice here. If you want to find the time or the amount at time 18, a lot of people like to isolate that quantity, and so they'll add the A of 0 over in the front. And so they'll say something like, right, which actually makes a lot of sense. The amount of water at time 18 is the amount of water you started with, the initial amount at time 0, plus the net change, right, in the amount of water in the tank from 0 to 18. Okay, so I'm right. Notice I did not write the expressions for W of t and R of t again. I just wrote their names because I'm not doing this by hand. There's no point in writing all that. It's a waste of time. So this is what? This is 1,200 plus, right? And this integral I'm going to put in my calculator. Since I defined I defined W and R of t, right? So I can use that here to help me. So I'm going to type in the word int. I'm going to put my limits of integration. So that's 0 up to, it's hard to click. I guess I'll have to use the arrow key. Yeah, unfortunate. So now in the integral, and I should put parentheses here, I'm going to put w of x, which is my rate in, minus r of x, which is my rate out. And I'm going to put a dx, right? Because if I don't put dx, nothing happens. So dx, and there is my calculation. I'm getting about 109.788 we could put down. So don't forget about that initial amount, right? Because that's not your answer. That's just the net change. The change in the amount of water from when you started over that 18-hour period. So that was 109.788. So, oops, wrong way. Okay. So in total, right? And so they said to the nearest gallon. So maybe now I will do my rounding here. So it'd be 1,310 gallons of water at time 18. Cool beans. Okay. So not bad. I do have some work to do, but I think really what you want to pay attention to in this question is the conceptual aspect that the derivative amount of the amount function, which by the way is not mentioned here, and so we have to sort of create a function, is the rate in minus the rate out. Okay, part C, everybody's favorite question. At what time, t, on the interval from 0 to 18, right, including the endpoints, is the amount of water in the tank an absolute minimum? Show the work that leads to your conclusion. Okay, so right, like I was mentioning in class, you know, the minute somebody asks for absolute max or minimum of any quantity, you may as well just make that table immediately, right? The candidates test, we call it, which is nothing more than an input-output table. So it's certain times I have to check, and what are you trying to find the max or min of? The absolute min-max of the amount of water. So the function you're looking at is not like w of t or r of t, it's a of t. Okay, now, and the other thing is immediately I know that like I have to check the endpoints of the interval, of the closed interval. So you should put those down immediately. Notice though, you actually already have those values. At time 0, we were given the amount was 1200. So I might as well put that there. And also in part B, I actually calculated the amount at time 18. I don't need to show that again, but I will put the value in the table, right? The thing I have to check, and I have to explain myself on this, is are there any critical numbers inside the interval from 0 to 18 such that the derivative of a of t is 0, and are they relative minimums? Remember, it's possible that a relative minimum could be your absolute minimum. So I have to check for critical numbers. I have to check for the critical numbers of a of t. A of t, if I want its critical numbers, I have to look at its derivative. Its derivative is a prime. And earlier we said that a prime is w of t minus r of t. If you do not write that you taking this quantity and setting it equal to 0, you automatically lose a point because that is how you are locating your critical numbers. Now, on Desmos, I've already graphed w of t minus r of t. So let's go back here for a second, right? And I can hide what I don't need, but I want to actually see the black graph that's already on. So, and if you want, I mentioned this before in class, you could restrict the domain here because you actually really don't want to, look at stuff that's outside the domain interval. That tends to get confusing. So I'll actually put that I only want to see this rate function from time 0 to 18. So my braces should close automatically. They do. So I'm only seeing this function where I want it. So I could see that between 0 and 18, there are two critical numbers, 6.49 roughly and 12.97. I need to write those down, but I also want to pay attention, and right now, so I don't have to keep going back and forth, which of those critical numbers is a relative minimum or relative maximum. Remember, right, you're looking at the graph of the derivative. So you're analyzing the way the signs of this graph changes around those zeros, which are the critical numbers. I could see that the sign of my derivative at 6.49 goes from negative to positive. And at 12.97, the derivative is going from positive to negative. So, right, only 6.49 is a relative minimum. I will still mention the 12.97, but there's no way a relative maximum could be the absolute minimum. And the way you get away with not having to check that is by saying that here, right? So I set W of t minus R of t equal to 0. And then right after that, I might put like an implies arrows and say, here's the values of t I found from my calculator. So, and again, I would keep a few decimal places here because you have to be careful. I am going to do something with at least one of these numbers in the candidates test. So you don't want to round too much. Keep some decimal places, but it's 6.4948, and then also it was 12.9748, I believe. Should be good. Now I'm going to say at t equals 4948, right? The amount, right, has a relative maximum, right? The amount of water in the tank is at did I say relative maximum? Excuse me, I meant relative minimum, right? I care about the relative min because I'm looking for the absolute min. I don't particularly care about the relative max. So that would be a relative min because, right, what happened? Because W of t minus R of t, which is the derivative, the rate in minus the rate out, changes sign from changes sign from negative to positive at this time. This, I know you're like, oh, I just need to make the table. No. You need this, right? You need to find the critical numbers that could possibly be the absolute minimum. It's required, and I need to show how I found them. Just notice how this rate in, rate out expression, though, is so pervasive throughout the question. All right. So that means the only other candidate I have to worry about here is actually this one. I don't have to check the 12.97 because there's no way that it's going to be a relative absolute min. It's a relative max. Okay, and so I have to calculate what the amount is at this time. I have the other ones already. What's nice about doing part B is this actually shows you exactly how to calculate the amount of water at any time t, right? And so when I want the amount of water at this time, I am going to use my calculator, but I need to show in the table how I'm calculating it. So I'm going to write here that A of 6.4948, the amount at that time, is the initial amount, which was 1200, plus the definite integral from 0 up to that time, right? You notice, and this kind of takes you a little bit back to the beginning of all this with the first fundamental theorem of calculus. Do you see where the time input ends up? It ends up as your upper limit of integration, which is something we saw quite a bit. So, and what are you integrating? W of t, rate in, minus R of t, rate out. Cool. And I'll put my answer here once I get it from my calculator. So I already have an integral here. And if I want, I could put that 1200 in front, like, because I just want the final answer here, right? I'm not trying to play games. The only thing I have to do is change the time, right? I have to, which is the upper limit of integration, if I ever get there. There we go. Okay, so let's backspace that. And so it was 6.4948. So we get about 25 gallons in total, right? What that means is that, right, during that time interval, there was a lot of more water leaving the tank than there was coming in. You started with 1200, and over that time, you're down to 525. So not only did like the water coming in went out, but so did the water that you started with. So that looks like the smallest, right? 525. Do they say to the nearest whole number anything? Well, they asked for the time, right? So the time would be the 6.4948, but I do need to write here that this is about 525 gallons, okay? So I'm going to say, therefore, the absolute min amount of water in the tank on, so at the time interval, because remember, when you look for those absolute mins or maxes, you're always looking for them on a closed interval. So on that interval occurs, or happens at, right, occurs at time t equals 6.4948 hours. Cool. So I think, right, what we see here too is that parts A, B, and C are extraordinarily standard questions, which means what? Which means that if you practice and think about these things, you can get very efficient with them. That's not to say that questions on AP exams are just gimmies. I think this stuff is hard. And also, some questions are a little out of left field, curveball. So last one here. For time t greater than 18, water is no longer pumped into the tank, but water continues to be removed at a rate r of t until the tank becomes empty. So water is only leaving the tank, right? There's nothing coming in anymore. Let k be the time at which the tank becomes empty. I see where this is going. Okay, right, and here's an interesting prompt that we're going to see quite a bit here coming up in the next couple of weeks, maybe most of the unit. Write, but do not solve. So they want me to set up an equation involving an integral expression that can be used to find the value of k. So they want me to set up a correct equation that has an integral expression that lets you find that time when the tank is empty. I don't have to solve it. I don't really have to do anything with it. I just have to set it up. So these can be tough because if you don't think about this correctly, it's kind of hard to get it right. So here's what's happening, right? At the moment after time t equals 18, so right after 18, the water in the tank coming in is shut off. And so, but there's still water pumped out. So I do notice that, right, at time t equals 18, I do see that this is the amount of water that was in the tank. Luckily, I have that because if I didn't, I'd have to go find it. What I would say is, though, the people that make up these questions can be pretty kind in that way that, look, you actually have most of what you need to accomplish this question. You just have to piece it together correctly. So, right, like there's 13 or 1,310 gallons in the tank when the water coming in is shut off. And all that is happening now is that pump out is just on. So just this is on, pump in is off. So I could think about this a couple of ways, right? But if you have 1,310 gallons left, how long is that going to take to go out? Well, it depends on your rate out, right? But your rate out is R of t. So I could write that, look, you're going to have to take out all this water you had, and I have to subtract out, right, how much water is being pumped out at a rate R of t. Now, this starts to happen at time 18. When is it going to finish, right? Well, they said it's going to finish at some time k. When is it? I really don't know, but here it would be the upper limit of integration. So think about this. The water left in the tank, take away the rate at which, or rather the integral of the rate at which water is pumped out. When is that going to be 0, right? When will the amount of water left in the tank be nothing? So I have to set it equal to 0. That's one way I could write it. The other way you could kind of think about this too, right, is if you move this integral over to the right-hand side, you obviously get an equivalent statement. Some people think about this a little bit better when it's written that way. So you have your 1,310 gallons. Remember, I'm adding this over. If I add it over, I'm saying it's equal to this integral, right? And so the question really is, how long is it going to take for this function to accumulate enough water being pumped out so that it pumps out the remaining amount of water? So either of these two equations that I wrote here, they both say the same thing, but I think that when you construct them, you think about them a little bit differently. Either of these two equations, if I put these two down on my paper with the k as the upper limit of integration, that time k they're talking about, you would get full credit for either. Cool beans. So, we don't have our second class this week. There are some quick multiple choice calculator practice. And if you want, besides what's on the homework, down here, I have another rate in, rate out question. I highly recommend you take the time to do this. And I'll have my notes up. Other than that, you know the deal. If you have questions, hit me up, but definitely practice your rate in, rate out. Take care.